everybody. So multiple linear regression. Sometimes we have one continuous factor, and we also have multiple continuous predictor, and we want to find a linear relationship or a quadratic relationship between this y and your predictors. We said, okay, this is basically two examples. One is a straight plane when you don't have any interactions. Here you have interaction between these two predictors, then it's kind of like curvature. If you want, you can add the quadratic effect as well. For example, x1 squared or x2 squared, and so on and so forth. Okay? Then we said this is sort of like a scalar representation. We can have a more compact representation using matrices. So X is the matrix of your predictors. So first predictor, different columns represent different predictors, and different rows represent different samples that you have. Okay? If you have 10 samples, 5 predictors, then it would be 10 the number of rows and 6 the number of columns. Why 6? Because we have also intercept, which we are going to replace with ones. So that ones, that column with one value, is basically the values of 1 is basically for intercept. You have a vector of coefficient to be estimated, and you have also vector of random noises. And y is the vector of responses. We want to minimize this square error. So this is the error, random error, the squared, which is this guy. For that, we take a derivative with respect to beta. And then this is going to be closed form solution or estimator for beta. X transpose X inverse X transpose Y. We had one example. We showed that how we can find X transpose X. In this example, we have 2 variables and 1 intercept. So we are going to estimate beta 1, beta 2, and beta 0. And as you can see, this is X transpose X inverse. X transpose Y is this guy. You multiply these two, and then you get your beta 0, beta 1. This is beta 1, and this is beta 2. Okay? Any questions? So can anybody tell me what is the interpretation of, let's say, beta 1? In this case is 2.74. What is the interpretation? No, that's beta 1, not beta 0. Anybody? Yes?
Some measure of the relative sensitivity of that variable.
So can you tell me, I agree, this is kind of some measure of relative sensitivity of that variable. But can you be more clear? What does it mean?
So if you were to increase x1 by some small amount, you have a bigger impact.
So let's say one unit.
Then it would go up by 2.74.
Exactly.
Whereas if you raise x2 by 1, it only go up by that factor.
Exactly. So what does it mean? It means if you keep all other variables constant, okay, and you increase x1 by 1 unit, the amount of change in y would be this number. Okay? Does it make sense? If you keep all other variables constant, and if you increase x1 by 1 unit, the amount of change in y is this coefficient. Okay? You can do say the same thing for beta 2. So if you keep basically x1 constant, then you increase x2 by 1, the amount of change in y would be this number. Is it clear? Any questions? So which one do you think is more important, x1 or x2? x1. Everybody agrees? That's not correct. Because the scale is different. You cannot simply compare this coefficient with this coefficient. The scale is different. If I go back to, look at the range of x1s. It's very small. x2s are very basically large. So you cannot simply compare them. In order to compare them, you need to either first scale your X matrix, then do the regression. By scaling, I mean subtract mu, divide by a standard deviation. Okay? Either do that, or you need to divide each of these coefficients by their standard deviation, and then compare that one. Okay? I'll show you that the second method when we are doing basic hypothesis testing. But is it clear why we cannot compare beta hat 1 and beta hat 2? Okay? Okay. So the question is how we can estimate sigma squared. And as you know, we can use basically the error. And so the error is each observations minus prediction. We get those errors, we square them, we add them up, divided by n minus p. Why p? Because we are estimating p parameters. So in this example, p is what? 3. 1 for intercept, 2 for variables. Okay, so we have 3 coefficients to estimate. And so now the question is, let's say you have a vector of coefficients, estimated coefficient, which is, in this example, beta 0, beta 1, and beta 2. So you remember, this is estimator. Estimator is a random variable, and it has some properties. It's a random variable, so therefore it has mean and variance, like x bar. Remember, x bar is estimator for mu. It has a mean, which is mu, and it has a variance, which is sigma squared divided by n. Now the question is, what is the mean of this estimator? What is the variance of this estimator? So we can show that this is an unbiased estimator for mean, which means expected value of your estimate is the same as the actual parameter. So on average, you are, I mean, if your sample size is very large, then you basically catch the truth. Okay? How about the variance? The variance of beta hat, as you can see, is x transpose x inverse sigma squared. So this sigma squared, you can estimate it using SSE divided by n minus p. Okay? Like previous slide. If you don't have it, and this is x transpose x inverse. This gives you basically the covariance matrix for beta. So what do I mean by covariance matrix? So this covariance matrix has some elements. By the way, let's call this guy matrix C, because this is a matrix. Okay? This is a symmetric matrix, and the elements are C01, C02, C10, C11, C12, C20, C21, C22. Okay? So, and this is multiplied by sigma squared. This gives you variance of beta hat. This is a vector. So the diagonal element gives you the variance of each component. Okay? So for example, variance of beta 0 hat would be C00, this element, multiplied by sigma squared. Variance of beta 1 hat is C11 sigma squared. And variance of beta 2 hat is C22 sigma squared. Okay? Now, how about this guy? Do you know what this is? This is what? Covariance of these two coefficients. So what is the covariance between beta 0 and beta 1? Actually estimate. Is the same as covariance of beta 1 hat and beta 0 hat. They are the same. And it is C01 sigma squared, which is the same as C10 sigma squared. So the off-diagonal elements, these are the same. These are equal. So it's kind of like a symmetric matrix. The off-diagonals are related to covariance. which means whether they are changing together or not. If one increases, the other one increases or not. Does it make sense? Questions? Yes.
The sigma here is referring to the standard deviation of.
Yes, exactly. You remember our original model was y is x beta plus epsilon, and this epsilon is NID 0 sigma squared. That's the sigma squared. Yes. So, any other questions? Yes.
Variables. How does the covariance between the two variables compare to the correlation?
So the question is the correlation coefficient that we started, like rho, for finding the correlation, for example, between y and x. How this is related to this guy here. So they are related, but this is a little bit different. Over there, we were talking about the correlation between x and y's. Okay? Here, we are talking about correlation or covariance of their coefficients. Okay? So, do we use it in this class or in practice a lot? No. What we usually use is the diagonal element. Okay? We care more about the variance of these two rather than the covariance of these basically elements. But I just want to tell you what these basically values mean. Okay? So it means if your beta 1, okay, increases, if it is positive, your beta 2 probably increases. Okay? Which means, let's say you have one sample, you estimate beta 1 and beta 2. Okay? You have another sample, you estimate beta 1 and beta 2. You repeat this for 100 times. Then if you plot the correlation between beta hat 1 and beta hat 2, then if it is positive, this is going to be positive. Does it make sense? So it's different from y and x. Now we are talking about the correlation between the estimated coefficients. Yes?
X1 and X2 are in different scales, you can standardize. So does that change the error if we standardize versus not standardize?
No, it doesn't. I mean, the question is standardization of coefficients. In order to be compare them, we need to standardize them. So does this standardization affect the error? No, it doesn't. So what we do is basically you are just scaling your X matrix. So error is in the relationship between X and Y. Do you know what I mean? Any other questions? Yes.
Does X have to be a square matrix? Is it like
no, definitely. Actually, the dimension of X is n by p. Yes, exactly, and it is. Okay. It always is because it's X transpose X. Yeah, actually inverse of that. Yeah. So X transpose X is always a square matrix. You had a question?
You were talking about the effects of beta 1 and beta 2, but you pointed towards the covariance 221100. Isn't that just between the same beta? Wouldn't you need like
no. This one is not the relationship between those two variables. This is just for one. This is just the variance. It's not covariance. Yeah.
To
yes,
describe
exactly.
that. Okay.
Yeah. Yes. Okay. So why do we need this? Because I have the point estimates here. If I know the variance of each point estimate, then I can find what? Confidence interval. Okay? That's what we did. We know that the point estimate is x bar. The variance of x bar we know, then we could find a confidence interval for mu. That's the same thing here. Okay? So I know that's the point estimate, and that's the variance of that. So that gives me a confidence interval. Since sigma squared is not known, we estimate it with this estimator. So your sigma squared estimator is MSE, which is SSE divided by n minus p. Okay? So you remember the confidence interval when variance is not known for mu? It was x bar plus minus t alpha n minus 1 s square root of n. You remember that? That's the confidence interval for mu. Now let's see. Instead of mu, I have beta hat j. Okay? T, instead of s divided by square root of n, because it was like the variance of x bar, or a standard deviation of x bar. Standard deviation of x bar is sigma divided by square root of n. We estimate sigma with s. Okay? So now we are talking about the standard deviation of, instead of this, a standard deviation of beta j. Okay? What is the standard deviation of beta j? Cjj divided by, multiplied by sigma squared, and then you take that one. Since I don't know sigma squared, I estimate that. So this is now Cjj sigma hat squared. Now I have T is alpha over 2. Alpha over 2, but degrees of freedom is different. This is n minus 1, but here it would be n minus p. Why? Because we are estimating p parameters. Is it clear? So very similar concept. Point estimator, the standard deviation of the point estimator along with t distribution. Questions? Yes.
So when we use like some statistical package, so they record like the p-values.
Oh, so the question is, when we use a statistical package, we get some p-values. No, I haven't covered that one yet. But you will, I think some statistical packages give you the confidence interval. But the p-value is based on the hypothesis test, which is going to be the next slide. Any other questions? Yes.
Relation don't capture one of the factors. So let's.
Oh, I see what you're saying.
Is there the error is higher, but it's like is there
Yes. Yes. So what happens? That's a very good question. So the question is, I just repeat to make sure that I understood the question correctly. So the question is, let's say your y in reality depends on 5 factors, but you only capture 3 of them. You only included 3 x's instead of 5. Okay? What's going to happen? So what happens is your variance of error is going to be larger compared to the case that you have 2 other factors. Okay? So the question is, can you basically, based on, maybe you don't know 2 other factors. Can you find, I mean, if you are lucky, yes, but not always. So what you need to do, you need to include as many as factors as you can, like, and then do sort of like variable selection or hypothesis testing, see which variable is not significant and exclude that. Okay? No. There is no threshold for that. But one thing else you can do is, so there is no threshold on the sigma squared, for example, to say if it is large, so you are not including one variable. So, but what you can do, for example, if you have some like candidates, okay, let's say you have 5 variables, you only included 3. What you can do, if you find the residuals, and then plot the scatter plot of residual versus those variables that you haven't included, if there is any relationship, it means that there is some information in the variables that you haven't included. That's, again, for the case that you know your potential pool. If you don't, no, you cannot do anything. Yes?
With different variables, or with adding something.
Yes, what? Yeah, I think I'm not going to cover in this class, but one thing is if you take the regression class, there are some variable selection methods, okay? So it's kind of like forward selection, backward elimination. Forward selection, you have like, let's say you have 100 variables. You just start with one and try to add more variables which increase the predictability of the model. Backward elimination is start with the whole and then try to remove those variables which don't affect, okay? And there are some other new techniques like lasso. Some of you may have heard of that. This is kind of like more more advanced technique in terms of variable selection. But again, we are not going to cover in this class.
Your error or
Yes, yes. So if your so what's going to happen if your residual error is very large, like sigma squared? Then in some cases, what happens is your confidence interval is very wide, and that could affect basically the hypothesis testing as well. Any other questions? Good. So let's see. Now back to your question. What if I want to do hypothesis testing? For example, what if I want to say whether beta j is like 5 or beta j is not 5? Okay? So can I do this hypothesis testing or not? This is the case, as you can see, whether beta j is equal to some numbers or not. You can find this value, which is sort of like a t statistic. So your estimate minus this number divided by a standard error, and the standard error is this guy here. You compare it with t alpha over 2n minus p degrees of freedom. This is for two-sided. You can have for one-sided as well. That's it. If it's greater than this, you reject H null. Otherwise, you accept H null. Is it clear? Any questions? So the p-value you see in the package is this one. P-value correspond to that basic hypothesis testing. So what is the, let's say, common value for beta j0? The right-hand side of hypothesis test. 0. Why? Because this hypothesis test can tell you whether this variable is important or not. Okay? So beta j0 and beta j is not 0. If you cannot reject H null, means your beta j that you estimated is actually 0, which means that variable is not significant in your prediction model. That's why you can exclude that variable. So the only variable selection that you learn in this class is this one. So you include everything in the model. You check the hypothesis testing. If it is 0, you exclude that. If it is not, then you put it in. You keep it in the model. Any other questions? Okay. So one example. Let's see. We want to test this hypothesis whether beta 2 is equal to 0 or not. So what we need to do, we need to find beta hat 2. Beta hat 2 was this number. Oops, sorry. 0.01253. This is actually from here. That's beta hat 2. This is beta hat 1, and this is beta hat 0. So divided by the standard error, this is C22, which is basically this element of X transpose X inverse. You multiply it by the estimated variance. You take a square root, and your T0 is this guy. You compare this one with T of alpha over 2, 0.025, and n minus p degrees of freedom. In this case, n is 25, I think. And p is 3. 25 minus 3. And this is 2.074. So your T0, which is 4.47, is greater than 0.74. Reject H null. Then, which means second variable is important. Okay? Any questions? So how about finding confidence interval for beta 1? So we need to have, we are actually using this equation. For beta 1, this is the estimated point estimator for beta 1, which is this guy, 2.74. T alpha over 2 is 2.074 times your standard error, which you already have it there. I'm just writing it again. 2, 3. And that gives you to basically lower and upper bound 2.55 and 2.93. Now, if I ask you this question, based on this confidence interval, can you tell me whether beta 1 is significant or important or not? What is it? It's significant. Why? Because it doesn't include 0. Okay? So the hypothesis testing, you remember we can do hypothesis testing using confidence intervals. If it doesn't include 0, then we can say, okay, H null should be rejected. This does not include 0. Therefore, beta 1 is also important. Okay? Any questions? So you remember I told you cannot compare beta hat 1 with beta hat 2, but you can compare their corresponding T0. So if you find T0, which is basically beta hat 1, standard error of beta hat 1, and T0 for beta hat 2, then you can compare these two values. Whichever is larger in terms of absolute value, it has like more effect on response. Does it make sense? This is what I mean by scaling. This is one way of scaling. Any questions? Yes. I mean, in terms of the absolute value. Because the magnitude is important, not the sign. Sign just shows whether, like, if one increases, the other one decreases. You know what I mean? It's just like the correlation. Okay? Any questions? We good? So there is another type of hypothesis testing that we can do. So that says whether all coefficients in the model, excluding basically your intercept, are 0 or at least one of them is non-zero. So if H null is not rejected, what does it mean? You cannot use these variables, these predictors, to predict y, because there is no relationship between them. Okay? So as you can see, if H null is not rejected, means all the coefficients are 0, which means no variables. These variables that you selected are not useful for predicting y. Okay? So what you do is basically based on ANOVA. So there are 3 sources of variation. One is basically error, the other one is total, and one is regression. So how much this basically here, this element regression, it explains how much of variability of y or response is explained by predictors. Okay? So that's related to that. How much variability of y is explained by your predictors or x's. This is captured by regression. The error is the remaining variability which is not explained. Okay? Does it make sense? And total is the total variability. So what I mean by that conceptually is this. So let's say this is y, this is x. And this is linear relationship. So let's say we don't consider basically x at all. So what is the total variation? So total variation means like put everything together and calculate sort of like variance. Okay. So if I project these points onto y-axis, okay, let's say, so total variability is something like this. It's a big variability. But some of this variability is captured by the relationship between y and x. So what is remaining variability is this part. Okay? Which is residuals. So that part is the error. Okay? So the one that you capture is your regression. So if regression is not important, which means there is no correlation between y and x, so this line is not important. Your total variability and the residual variability going to be the same. Okay? Does it make sense? Because this cannot explain any variability. Here, if I remove this line, the residual is going to be, so let's say this is residuals. Residual is going to be something like this versus x. This number, this number, this number, these are very small. Actually, to be honest, it should be around 0. So something like this. Okay? So compare this variability with this variability. So the difference is the one we captured with variance. I'm sorry, with regression. Okay? Here in this case, we are not capturing anything with regression. Any questions? Yes?
I guess the total variability or the variability just in y that you were mentioning, is it the range?
No, actually, it's related to range. It's not exactly range, but it's this one. Let's say capital N. So it's, no, this is y bar. You know, like forget about error, okay? So let's say I'm giving you just y, and I tell you like calculate the variance. So that's the numerator for variance. Like s squared. Okay? So I'm not considering any x here. This is just like only y. Okay? So we have this sum of squares. I tell you how to calculate them. Then we have degrees of freedom. Degrees of freedom for error is n minus p. For total is n minus 1. And degrees of freedom for basically regression. This is wrong, actually. This should be p minus 1, actually. Yes. Your k, yeah, actually, it's right. Yeah. No. Because your k here is defined as p minus 1, excluding your 1 variable. So k is p minus 1, the number of predictors that you have. Okay? So mean square of regression is SSR divided by k. So your MSR is SSR divided by k. Your MSE is SSE divided by degrees of freedom, which is n minus p. Okay? Then you get your MSR and MSE. You can find your F0, and you compare your F0 with what? Anybody can tell me? What is the critical value? F alpha and? Give me degrees of freedom. K and n minus p. Exactly. So one example. Oh, by the way, how we can calculate sum of a square of total. So these are the equations. SS of total, as you can see. Oops. Over there is y transpose y. This is the vector. Minus summation of yi squared divided by n. Or, if you don't want to go vector-wise, it should be summation of y squared minus summation of y squared divided by n. This is vector notation. This is individual notation. So in this case, as you can see, in our example, y transpose y is this guy minus this component. It gives me 6105.94 for sum of a square of total. How about sum of a square of regression? So you use beta hat. This is vector of beta hats. X transpose matrix times y minus summation of yi squared divided by n. So this is vector. This is a scalar. Okay? And your SSE would be SST minus SSR. So as you can see, this is a sub-regression that you get, and this is a sub error. You put it here. How about degrees of freedom? Degrees of freedom for this guy is k. K is the number of predictors. So actually what we are trying to do here is this hypothesis testing. H null, whether beta 1 and beta 2 are 0, H alternative is otherwise. At least one of them is non-zero. Okay? So basically this tests whether regression is useless or not. That's it. If you cannot reject H null, it's useless. So your P is 3 because you are estimating 3 parameters. Your K is P minus 1, which is 2 in this case. And your N, I think, is 25. So therefore, your degrees of freedom, this is K, which is 2. This is N minus 1, 25 minus 1, 24. And this one is N minus P, which is 25 minus 3, 22. So mean square, this guy divided by degrees of freedom, and this guy divided by degrees of freedom. So F is the ratio of these two mean squares, and you get this F. You compare it with F of 0.05, 2, and 22 degrees of freedom. And this number is way too large, so it's definitely significant. As you can see, the p-value is very small, it's close to 0. So which means that at least one of the coefficients, one of the predictors, so when you reject H null, it means this. At least one of the predictors is significant in predicting y. At least one of them. Okay? Any questions? You good? Yes. Yeah, you can. Yes, for example, LSD, if you want to do, you can do LSD as well here. Yes, that's a good question. The question is, can we find which one is different from others? Can we use LSD? Yes, you can use LSD here. Or you can do individual ones as well. Okay. Okay, confidence interval on mean. So you know how to calculate confidence interval. You learn how to calculate confidence interval for beta. But what if we want to find the confidence interval for mean of the predictors? So basically, we know that this is our model. Okay. Then we estimate y hat, okay, by x beta hat. So this is point estimate for y, okay? So what if I want to do that point estimation for some values that I have, let's say x0, then it would be, let me put it this way. So x0 is a vector, so it would be x0 prime. This is a matrix. Just want to tell you what I mean by that. So this is x11, x12, xn1, x21, x22, xn2. So this is the X matrix. So by x0, I mean one row of this, for example. Okay? If this is x, by x0, I mean one of these x values. Okay? So if I have this row, I can find the estimate for y, which is this guy. This is a scalar. This is a vector transpose times a vector. So it's an inner product. This is going to be a scalar. Okay? Or this is the same as saying beta 0 plus beta hat 1 x0 1 and plus beta hat 2 x0 2. That's the same thing. Okay? So what is this? This is point estimate. And you remember I said like point estimate of y given x, because regression is y given x. So we are estimating this mean. This is a point estimate. Can I have a confidence interval for that? Not just the point estimate. So the point estimate is the line, regression line. Can I have a confidence interval around that? Okay? So that's the equation for confidence interval. So that's the point estimate line, and this is the variance. So if I know mean and I know the variance, I can find the confidence interval. Exactly like a t distribution or x bar. So that's the point estimate, which is this guy, and that's the standard deviation. Okay? And again, t with alpha over to an n minus p degrees of freedom. So here is what you see. This is the line. So this is for one variable, actually. Y versus x. So this is the line, which is the point estimate. And based on the variance that they have, I have this confidence interval. So what is unusual in this confidence interval? What is it? Exactly. So the confidence interval is variable. The length of confidence interval, width of confidence interval is variable. So what is it? I mean, it has some kind of like pattern. It's not random variable. What can you say from this figure? What else can you say? Exactly. So what it says, when you are closer to the center, you have more precision, which means the width of confidence interval is smaller compared to the boundaries. Does it make sense? Do you know why? No, not because of the more data points. Actually, it could be related to more data points as well, but there is a mathematical explanation for that. Anybody can guess.
It's kind of like your points need to be bounded.
Yes, that's a good explanation in terms of that's what you also said. You have more basically data points in the middle in both sides. However, if you go to the right side, you have, for example, here, you don't have any data points on the right side. Here, you don't have any data points on the left side. But again, you are in between. It's kind of like balanced. Conceptually, that's good. But mathematically, also, there is a reason for that. So that x transpose x inverse sigma squared, okay? In order to explain that, I'm going to use just one variable. For one variable, let's say this is for more than one variable. Let's say we have only y and x. This can be reduced to sigma squared which is S of, you remember SXX? Do you remember that? This is kind of like equation for SXX. So if your points are closer to x bar, what's going to happen? I'm sorry, it's the other way around. Yeah. Yes. It has some relationship between, I guess so, yeah. So if your point is closer to x bar, then what's going to happen? This difference is smaller. So your variance gets smaller. When your variance gets smaller, what's going to happen? These two limits going to get closer to each other. When you get far from your middle point, then this distance gets larger. Okay? When it gets larger, your variance increases. Therefore, when your variance increases, your control or confidence interval gets farther from each other. Yes? No, I mean, it doesn't matter because you have always x bar. What we mean center is not 0. What do we mean by center is the center of x bar. It could be 0, it could be 2, it could be 3. Do you know what I mean? So, like, no matter what your mean is, it's centered around mean. Yeah, right? Any other questions? Okay. So here is one example. So here is the data that we have. If I go back very quickly, this is the data that we have, and we want to find the confidence interval for one of those x's, which is 1, 8, 1, 10, I think. Right? I'm sorry, 1, 8, 275. One of those x's. Let's see, just want to make sure that it's here. 1, 8, 275. Do we have it here or not? We should have it, no? 295, but that one is 18275, I guess. Yes. Huh. That's interesting. I guess I stop here to figure out what's going on. We only have 1 minute. I'll see you on Friday.